So now we're talking about copy on write. This is a standard or very popular technique for OSs to optimize. And it's kind of a lazy evaluation as well. So, and the context is in fork. And remember, fork, logically speaking, makes a clone of the parent process itself and as child, right? The child runs exactly where the parent left off, right, after the fork, except the fork has a return value 0 if it's child, and the process ID if it's the parent. Or the child's process ID has a return value if you're running as parent. And so the child doesn't run from beginning, it runs from the point of the return of fork. Now, so logically speaking, you modify, right, so if you do a fork, right, you make a copy, but do you really want to make a copy? Well, if you can do lazy evaluation, that can save you a lot of unnecessary copy, right? So what copy on write does is when you fork a child, the child initially shares those same pages as the parent, but with a condition. So as long as nobody makes any changes to memory, then you're okay, right? Because there's no difference. You can't tell the difference anyway. But as soon as anybody attempts to make a change to the page, right? So it could be child trying to make a change, parent could try to make a change, anyone. Then OS takes over and says, oh, no, sorry, before you make the change, let me unshare the page so you can modify your own copy, okay? So that allows you to do kind of a demand copying, so to speak, right? So you don't make a copy of a page until needed. And the time needed is first modification to a page, okay? And so that, how can you do it? Well, you can mark a page as read-only, and when you attempt to modify a read-only page, hardware traps the OS. OS can say, oh, it's not really a read-only page. It's really a copy-on-write page. Then it makes a copy and then updates, restores, right? So that can be done pretty easily. So that way, also with the, I mean, that's not the only way to do fork, but that's one very popular way to do it. Now, also in the case of zero fill on demand, like I was just talking about, the pool should always have some free frames, okay? And then that way, that's what allows the pager to be able to have a much easier time, and also reduces the latency. So so how can you do it? Well, there are a couple of ways to do it. So maybe during idle time, the OS can do what's called a reaper, and that actually is coming up later, to save some processes and put them on frame list so that you keep a minimum threshold of pages in the, or I should say, frames in the free frame list. Okay, so anyway, copy on write. So initially, parent, child share everything, but then when one of them, whether it's parent or child, makes a copy, then it gets a separate copy. OS makes that copy and then updates the point, the mapping to the copy. Okay, so they can continue sharing as much as possible. Now, another alternative to copy on write is vfork. Now, V, of course, stands for virtual memory. So this is a little different in that it does it even more aggressively, but somewhat dangerous. So in the sense that when you fork a child, the parent process is put on suspense. So it's suspended while the child runs. And the child basically runs in exactly the same address space as the parent, and there's no copy on write. It can make the copies all it wants. I mean, this may be not too bad because, well, because the child is a clone of the parent. The parent, as long as the parent is written in a way it knows what it's doing, then it does have full control over what the child does, right? And so if the child makes any change and then finishes, the parent actually gets resumed and you can see all the changes made by the child. But if the child calls exec to replace itself, that's when that sharing stops. Okay, so this can be actually kind of nice because there's not even the complexity associated with copy on write, because copy on write does cost you some bookkeeping, right? It's not free. Whereas vfork says, okay, I'm just going to trust the process itself. It knows what it's doing. It's forking itself anyway. And so it's running, it's written in a way that it knows what it's doing, so I'm just going to allow it to make modification. And when exec happens, it replaces its own image with a new executable, and so parent is not affected. Okay, so that is actually a newer trend in doing fork. Okay, so now I'm going to talk about page replacement. So page replacement is when you need a frame, but there's no frame available. They're all in use by some page. So that means you got to pick a victim and say, okay, I want to be nice, but you guys are all stubborn, so I'm going to pick a victim by kicking somebody out. And that's called a page out operation. That by kicking them out, that means saving their content to disk, so the frame can be recycled and reused. Now, to do this, hardware would keep a dirty bit, and you've seen dirty bit in different contexts. Like caches have dirty bits, pages can have dirty bits too. So if it's dirty, that means you do need to do a page out operation, right? That means save this content to disk before you can reuse it. But if it's not dirty, the content is already on disk. No need to save. You can just go ahead and reuse it, right? Zero it out and reuse. So two problems in demand paging are what's called frame allocation and page replacement. So page replacement is one. The other problem, page allocation, I'll talk about later. Now that's a different problem. Frame allocation says, now do I want to give a fixed number of frames to each process? Or do I want to make it flexible? When a process needs a frame, can it grab it from another process's frame, or can it only grab from its own frame? Right? That's a frame allocation problem. That's different from page replacement, which is to find a victim, right? Kick him out and recycle that frame. So here is an example. So now the physical memory is here, the kernel, and then you have these already in use by these frames are all in use by pages G, C, F, H, A, and C and E, right? And now when this process 1 wants to access page B, it looks up, oops, it's invalid, but it's on disk, so I want to bring in B. Where do I put it? It's already occupied by all the other pages, so I got to find a victim, kick them out, then load in B. Otherwise, you have no place to put B, right? So what can you do? So if there's a free frame, use it. If no free frame, pick a victim frame. Write the victim frame to disk if it's dirty. And then load in, put it in free frame, update its data structure, restart the instruction. Okay. Page replacement, find a victim. If dirty, swap out, and then swap the desired page into this frame, update the mapping. Okay. Now, so page and frame replacement algorithms include, so we talked about this, frame allocation, page replacement, right? So frame allocation, how many frames to give to each process. Page replacement says which frame to replace. But both objectives are, one, the lowest page fault rate on both first access and re-access. So to evaluate these page replacement algorithms, usually what's done is called reference string. That is, you have a sequence of these page numbers, okay? And so if you access things in the same page, well, that's the same page number in the sequence. And so that way, you don't need to do repeat. So like if page 7 gets accessed 100 times, you don't have to say 700 times, because once it's in there, you don't cause a page fault, right? It's a repeated one. So then you compute the number of page faults on that string or that sequence of page numbers. Okay, and so as you can imagine, if you it depends on how many frames you have. That has an effect on page faults. So this is kind of what you expect. That is, if you have more frames, your page fault rate is going to decrease. Right? At some point, you don't even have to page out, so no page fault. Right? But most likely, you don't have that many frames to serve the demands of all the pages, so you're going to have some page faults. But this is the trend you would expect. But is that always the case? Well, not really, because there could be some anomalies, which we'll talk about. But anyway, it depends on the policy as well. So one policy or scheduling algorithm or page replacement algorithm is called FIFO. And so in this case, you just go around in the cycle, right? So reference string 7, 0, 1, and then the next one comes in is 2, so it wraps around. 7 gets replaced by 2. Next one is 0, so 0 is not used. But then the FIFO pointer is still pointing at that. So even though 0 was just accessed, 3 comes in, 3 is not there, page fault, so then 3 goes into where the 0 part is, and the pointer moves on to the next one, and 0 is used again. Oops! So it just got kicked out and brought back in, right? And so that replaces 1, and then 4, then it wraps around, that replaces 2, but then 2 is referenced again. Oops! So as you can see, FIFO is kind of blind to the future in the sense that it would be nice if you know 2 is going to be referenced again, so you don't page it out, right? But it doesn't know that. And so that way, there are a couple cases, really you might call unnecessary page out, page in, right? So it got replaced and then got brought back in again, just to a different frame. And then 3, 0, and so you can see, right? So, and now you can also have other reference strings, and so the number of page faults could be different. Okay, and if you have more frames, page faults could be different too. And so you just use a FIFO-Q or really a circular pointer, like a circular Q. So that's easy to implement, very easy to implement. But just having more frames doesn't automatically lead to lower page fault. And this is Bilaty's anomaly. So Bilaty is a pretty well-known Hungarian computer scientist. He worked at IBM for a while, developed a lot of these important techniques, especially with paging, and also later worked on, I think, Asian language, and then he later became CEO and president of Mitsubishi Electric Research Lab, MERL. So he was the first one to point out this anomaly, where if you are using something like a FIFO-based algorithm, by increasing the number of frames, you actually could see an increase in page faults, which is like, what, really? Counterintuitive. Yes, that could actually happen. So that's so instead of the curve dropping over the, as you increase number of pages, it actually could temporarily increase before going down. Okay, and so that actually could happen. And so one that devised the OPT or optimal page replacement algorithm. So the optimal one, OPT, is a lot like these scheduling ones where you have to know the upcoming. You have to have a little oracle or knowing what's coming up, which may or may not be the case. So in practice, this may not be implemented exactly because you don't know the future, but at least it serves as a lower bound, right? So what it does is it replaces a page that will not be used for the longest period of time. Okay, so that requires foresight. So like in this case, 7, 0, 1 you fill up, and then 2, well, Why replace 7? Well, because 7 is not going to be used for until so much later, right? But then 0 and 1 are going to be used earlier than 7. So 0 is used, and then 1 is going to be used much later. Well, 1 is used here, right? And then 0, and here there's a 3 that comes in. So now that's when it replaces the 1. So this does not have that anomaly, but because you can't read the future, that's really what it only is a theoretical lower bound, but not done in practice. But that doesn't mean you can't approximate it. So what's most common is least recently used, or LRU. And this is also the same case with caches as well, not just these pages. So this uses past knowledge to predict future, right? So it replaces a page that hasn't been used for the longest time. So that means you actually have to keep track of some kind of age information with each page in terms of its axis. And the axis could be you read or write, okay? And so that means you replace the oldest page in a sense, right? And this is generally a good algorithm and is frequently used. So LRU in this case, so instead of looking forward, you look back. 7, 0, 1, and then 2. Well, which is the oldest? 7 is oldest, so then you replaces 7. So 2 comes in. Now comes, and then 3. Between 0 and 3, but between 0 and 1 is older, so you replace the 1, and then that's where 3 comes in. But unfortunately, because it couldn't predict the future, well, there's some cases where it actually could be a little worse. But then in this case, it's actually okay, probably due to some locality. So it's actually good that you kicked out 1 instead of 0, because 0 will be used, well, actually right away. So good thing you didn't kick it out. Otherwise, compared to 5 kicked out the 0 and brought it back in, right? And then 4, well, replaces 2 because 2 was oldest between 0, 2, and 3. But unfortunately, it couldn't look at the future because 2 has to be brought back in the next axis, right? So, but okay, now it kicks out 3 because 3 is oldest, so places 2 there. Another unfortunate case where 3 is used right away, so then it has to replace the 0. And then unfortunate again, 0 is used in the next cycle, right? So it could get into bad case if somebody constructs it that way. But still, it's better than FIFO. It's not as good as OPT, okay? So it's only an approximation. And hopefully, if you have a large enough set of frames, you wouldn't run into this problem. Okay. So LRU can be implemented a number of different ways. One of them is what's called counter. But counter, what does counter actually mean? Well, counter, you can think more in terms of these, might say, timers. I mean, in 8051, you've seen timers, right? That the timer is actually not a clock. It's actually just a counter of your clock cycles, instruction cycles, right? So that's that sense of the counter. But here, it's really the counter value they're talking about. So that timer or clock is incremented not on every clock cycle, but on every memory reference. That's why it's called a counter here. Now every time the page is referenced, then that counter value, they call it clock, is copied out into the counter. Well, here, counter is think of it more as a field, a variable. Okay, so the terms are all kind of confusing, but just because the same word gets used many times. But you can think of it as that timestamp field, so to speak. Okay, so when you see counter, think of it as the timestamp variable, okay, associated with each page. So when the page needs to be changed, then you look at the counter, or these, so if need some, you then find this one with the smallest value and search the table. So that is how you can track kind of the true least recently used based on the counter value. But of course you have issues because counters are all finite. And what happens if you have to wrap around? Yeah, that could be an issue, right? Now if you don't want to have to deal with a wraparound issue, then you can use a stack, a data structure. So instead of saving the timestamp, what you do is you use the data structure in the form of doubly linked list to form a stack structure. So think of it as every time memory reference is done, you push, 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 push. What if it's already one that you already pushed on the stack? Well, you gotta pull it out from the middle of the stack and then push it on top. All right? That's what stack algorithm does. Kind of like a deck of cards. Push, 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 and oh, I've seen that one before. Look in it, pull it out, push it on top. Okay? So that's how you can update the least recently used. Okay? So that way, yeah, as you can imagine, there's more data structures to maintain. But then with the proper pointers, you could probably save this cost because you wouldn't have to do linear search into a stack. You probably already have a pointer in there into the middle of the stack, the node in there, and unlink, unlink, and link. So yeah, just more pointers to update. Okay, stack algorithms, LRU, OPT, no abilities, anomaly. Okay. So stack algorithm, as you can see, if you do reference string 47012, so these gets pushed, and then then there's update, right? So no, these are all then just before stack before A, well, the 7 gets referenced. So what happens? If 7 was in the middle of stack, so it gets pulled out and then re-pushed on the top of the stack. Okay, and because it's linked list, it doesn't have to do a lot of copying, just relink. Okay, there are a number of LRU approximation algorithms. So you say, really, another approximation? Yes, because the OPT is not possible to implement exactly, so you have to approximate it using LRU. But LRU itself, as you can see, is kind of hassle to have to do, and it's kind of difficult for hardware to do the linked list maintenance for you. So LRU would do want to approximate it at different levels. And LRU, even if you add special hardware, it's still slow. That's why approximation is done to enable faster implementations. And so there are a few of these. One is called single reference bit. Another is called additional reference bits. So that's built on top of single reference bit, but then keep track of more history. Whereas single reference bit is just 1 bit history. And there's something called second chance. That's a pretty interesting one that can use single reference bit, but then in a somewhat interesting way. So single reference bit, basically, you associate a bit called reference bit. So anytime it's a read or write access, that bit is set to 1. Otherwise, initialized to 0. And in case of finding a victim, what do? Well, you find from those with a reference bit of 0 because they haven't been accessed since the last time you tried, right? So of course, this is a very, very rough approximation because there could be lots of pages that haven't been referenced, but some are older, others are newer. How can you tell them apart? You can't. Okay. So, but this serves as a basis for other algorithms. Now, one would be what's called additional reference bits. So what does that mean? That means in addition to that reference bit, you actually save that, accumulate additional bits. So that means once in a while, maybe once every 100 seconds, not that often, but a few times a second, OS gets a timer interrupt, and all it does is collect these reference bits. And what it does is basically shift that latest bit from most significant bit into that 8-bit quantity. So basically, all the bits got pushed from to the right, right? And then the most significant bit is filled with the latest bit you read from the hardware reference bit. And that way, you have an approximate age, right? In fact, if it's 0, 0, 0, 0, 8 bits of 0, what does that mean? That means that in the past 8 samples, those haven't been referenced at all. So yes, that is actually true, right? That's a true non-use. But if you have 11000100, that means 1 is the most recent, and then the previous cycle, and then one before. And so compare that to the most recent one hasn't been used, and then 111. Right? So just looking at it as an unsigned number gives you an idea for the relative age, right? So that way, if it's a larger unsigned number, that means it has been used pretty recently. If it is a smaller number, that means it's an older page, right? So you want to pick one with the smallest history value, 8-bit history value as victim. But of course, you could have multiple pages with all zeros, and maybe there's additional consideration there, or maybe you think they're all equally good as a victim. There's one pretty well-known one called second chance algorithm. That's an LRU approximation. The way it works is it's kind of a FIFO, but used in conjunction with hardware-provided reference bit. And so the algorithm actually maintains a pointer in this kind of a circular queue, right? So what does it do? So it marches down these pages and then checks these reference bits. And of course, these bits are updated by hardware. So if it checks the reference bit, if it's 0, I'm going to just use it as the victim. But if it's 1, what happens? Well, that page gets a second chance. So then if it's 1, I clear it. And then I move I increment the pointer. Of course, when I hit the end, I wrap it around, right? So so that means by the time page, when you have a reference bit of 0, it's likely that it's already gone through one cycle and it hasn't been referenced after an entire cycle. Okay, so it is a FIFO, but it does have this consideration for recent reference. Okay, so you may have to march a number of times. So if it sees reference bit 0, reference bit 1 clears it and then marches. Continue to the next one. If it's 1, it has to clear again and then keep going, right, until it finds one that's 0. Okay, so, and in one case, it may actually, all of them have been referenced, which seems unlikely. Then it may actually go make one round until it comes back to the same one it just cleared, right? So it will terminate by definition, because once it's 0, and if you haven't found any other one that's a 0, by definition, you will come back to that very first one you marked as 0, right? So this will terminate. Okay, so this is a kind of a crude approximation of LRU, but it's pretty interesting. Okay, so that's how it works. Next victim, if it's 1, okay, clearly give it another chance. Marches down, it's another 1. Okay, fine. Set it as 0. And then marches down again, 0, good, I found my victim. Okay, so that's how it works. And in the meantime, these other ones can get referenced. Okay, so then they get another chance. Okay. So there's enhanced second chance algorithm, which actually consider the modification state. So why modification state? Well, because it's more expensive to have to replace a page that is dirty, right? Because you have to page it out. save it on disk before you can safely reuse that frame. So we do want to consider. So the best page would be if you consider this tuple of reference bit and modified bit. So reference 0 means not reference, 1 means reference, and then modified 0 means not modified, 1 means modified. So that tuple of 0, 0 is good, best choice. Why? Because it hasn't been referenced recently and it hasn't been modified. I don't have to do a page out. Good. That's my first choice. Now, if I can't find one like that, okay, then what's the second best? Well, the 0, 1, so that means hasn't been referenced, but it has been modified. Not quite as good because we have to write it out before replacement, but chances are it's not going to be referenced again, so we think it's a good one to page out and reclaim the frame. Now, what about the next one? So that is 1, 0. So you might say, wouldn't I want to prioritize the clean pages first? Well, not necessarily, because if 1, 0 means it's been recently referenced, but it hasn't been modified. It's clean, right? So the reason you might want to keep it because it is recently used, and in between read and write, there's probably more bias towards the read. You probably do more read than write. I mean, think of it like addition, right? You do 2 operands and read, and then 1 operand write, right? So so you have more chance of reusing a clean page. So even though its replacement cost may be a little cheaper, we still want to prioritize for another future reference soon. Now 1, 1 would be the least desirable to replace. Why? Because it's recently used and it's modified. And by principle of locality, what does that mean? That means it's likely to be modified again or accessed again. Yeah. The 0, 1 is preferred for replacement. That's because it's recently used but not modified. So the cost is it's not recently used and but modified, and so the priority here is biased towards recent use. Okay, so yes, you do have to pay a little bit of replacement cost, but you're betting on that it won't be used again. Okay, so now here this is definitely biased towards recent use. Okay, and so 1, 1 means if you replace it, not only do you have to flush, you actually may lose locality. So that's so you want to rely on second chance to prove that it's not going to be used again recently. Okay, so so as you can see, this is a pretty straightforward extension to the base second chance algorithm. Now, there's also what's called counting-based algorithms. And what are those? Well, you keep a counter of the number of references that have been made to each page. And so that is probably somewhat intuitive in the sense that you want to track how heavily used each page as opposed to whether it's recent or not recent. You just want to see its usage, right? Usage frequency. So there's one called LFU for least frequently used algorithm. So what does it do? So you basically keep a count. If every time you access, whether it's read or write, you increments count, right? And so you might say, well, this page hasn't been accessed a lot. I'm going to use that lower count as my criteria for saying that's probably a good victim, because if it hasn't been accessed much, it probably you're guessing that you won't miss it much, right? But then the problem is with the access pattern. Why? Because these access patterns are not uniform throughout the program. The program goes through phases. Upon loading, upon initialization, it has one behavior. And over time, when you activate different functions, different features, it may have different phases, right? Each phase may do its own, it has its own access behavior. So least frequently used may be suffering from a problem where initialization may bias certain pages that were heavily accessed during initialization, but after that, it's not touched on much anymore. So those tend to stick around much longer, even though those may be good candidates to replace. So the solution there is some kind of exponential decay. So we've seen that with scheduling as well. No, this doesn't know whether it's recently used. It only knows total number of times it's been accessed. So it has no idea about age. So even if it's recently used, but compared to one that's used a long time ago, this algorithm has no age concept at all, only the count. Okay, and most frequently used is kind of the opposite side, and it says, well, I'm going to try to guess or infer the age from the count, and small count means it probably got brought in recently, and I'm just starting to use it, so please don't kick it out. Right? So it's guessing kind of in the opposite way. But either way, these are not as commonly used in modern operating systems, but still good to know about them. Now, page buffering algorithm is one I mentioned a little earlier, which means you do want to keep a non-empty free frame list, so that upon this handling, you always have at least one free frame, if not more, to grab from and then to serve that page fault, right? And so you don't just wait until you really need to serve a page fault before you start finding the free frame. That's a little late, and that complicates your algorithm and adds the delay to the one that's just page faulted. So what do? Well, you can do a number of things. One is you can do what's called kind of predictive kind of flushing. So you would tentatively pick some victim, and then when convenient, right, when the OS is kind of idling, not doing much, so I'm just going to start thinking ahead and look for some possible victim. So this guy's dirty. Okay, let me flush them. So even though they haven't been paged out yet, you page them out first. So then what's a benefit? Well, they used to be dirty, now clean, because you flushed them, right? You save them to disk. So then next time, if you want to pick them as victim, you don't have to save them because you already saved them, right? They're already clean. So that's the one case, right? And from this, you can extend the idea. One is keep a list of modified pages. So instead of just one free frame list, you actually collect a separate list. These are all dirty pages, right? And then, so yeah, it's a slight variation. So you would then consider them, and then when the OS has free time, sneak in some flushes, and then once they're flushed, then they can get moved to a free frame list, right? So that way you don't mix them. Another extended idea would be, well, I don't do that zero fill, not just yet, even though they're on my free frame list. Why? Because you've seen the case where you evict a page and the next access you need them back again, right? Well, so if assuming you have enough frames and then you have the free frame list, the hope is that this is a way to make up for any bad prediction or bad approximation, right? Because this is not perfect, but at least if you keep it in free frame and you haven't dumped or wiped out this content, and that page is needed again, well, guess what? It's in the free frame list. You just bring it back, and you don't need to load from the disk. You haven't wiped out its content yet, so its content is still the same as the last time you was using it. Okay, so give it back to the original user. That way, it can be helpful and it reduces the penalty if the wrong victim frame is picked. Okay, so so that's one thing that is actually pretty effective. Okay, and now in addition to these kind of approximation algorithms, see, they are trying to do some kind of prediction, but no prediction is perfect. But can you do better than just OS trying to guess based on these mechanisms? Well, in certain cases you could, because if you know the certain characteristics of the application, you could actually do better. So what would be some examples? So some example may be like streaming applications, right? Most likely you want to keep streaming. Maybe in some cases, yes, you can do random access, move around, but then that would be one. Another may be databases. Especially, depending on how it's structured, it could be a relational database, could be something. They do have a certain access pattern, and so once you start a query, you could probably already figure out how the next couple of page access is. So you do have a little bit of future or look ahead, right? At least within that look ahead window. And so in those cases, then that knowledge can be valuable to this demand paging system. Okay, I mean, you don't have to do it, but if you do it, it can certainly perform better than just OS guessing. Now, it also has another benefit in that OS may try to do additional optimization. So you know the idea of caching, right? So OS may keep copies of the page in memory also as a I/O buffer, and it's really to improve its own performance. But application itself may also keep its own, may try to do its own caching as well. And so that is what's called double buffering. That's actually not a good use of memory resource. Okay, so that's one thing where having some application knowledge exposed to the OS can be helpful. Now, another, it has to do with whether you want to use a file system as your backing store or have OS access to its own swapping device. Now, swapping device would then not implement your file system structure. So no directories, no file names, no hierarchy, no inode or these metadata. You really just raw storage with minimal structure, and even buffering, it probably doesn't need to do that, or even locking, right? So it's raw storage. That way, it saves a lot of the overhead, because to maintain those metadata, you actually have to do the disk back and forth. Nowadays, you have SSD, so that's less of a problem. But still, when you switch to a different flash page, that also has some costs associated. So still, having raw storage access can improve the performance of the pager. Okay, next problem is the allocation of these frames. So again, this has to do with, do you assign a fixed number of frames to each process and allow the process to only access its own set of frames? Or do you want to have be able to get frames from a different process as is needed, right? And even if you have fixed number of these frames per process, do you assign the equal number of frames? So every process gets 20 frames, or you assign a variable number. Maybe some process gets 5 frames, some gets 200 frames. What's the right thing to do? Right? So those fall under the scope of these allocation of frames. So now these, and also there may be some minimum number of frames needed. Why? Because of architecture considerations. So IBM 370 has one instruction that has a special kind of move that may need as many as 6 pages. Instruction itself 6 bytes, which means it could cross page boundary, and it has the from and then from to for doing a move, right? But the from buffer could cross page boundary. The to buffer could cross another 2 page boundaries, right? So that means to even make it feasible for one instruction like this, you need a minimum of 6 pages. Otherwise, it's never gonna successfully retry, right? You need at least those 6 pages all in physical memory in order to successfully restart this instruction, or else it's just gonna page out, and then you never finish, right? So, now, what about the maximum? Well, maximum is you allocate all the frames to one process, but is that a good idea? Probably not, right? So anyway, so there's fixed allocation, priority allocation, and other schemes. So fixed allocation is further divided into equal allocation versus proportional. Equal means all processes get a fixed number, equal number of frames. So even if you don't need that many, I still give you 100 frames. And this other process, even if it needs a lot more, still 100 frames. Is that fair? Maybe, maybe not. Probably not the best idea. Okay, so you just divide up evenly, and then you keep some free frame buffer pool. Now proportional would be to allocate according to the size of process. So the address space of each process may change over time, right? And possibly as the stack grows, as you grow the heap and all that. So that could grow, and as you load in additional shared modules, right? DLLs, and so those are all part of your size parameter, and that changes as the process runs, right? Then you may use that as a guideline for deciding how many frames to allocate to that process. Now, priority allocation says, well, I want to define some priority so that certain processes with higher priorities will have an easier time, or would likely to get more frames, with lower priority would get, or would likely to lose frames or get replaced, right? So upon a page fault, OS would then look based on the priority of these processes, or where to look for frames to replace. So if a process has lower priority, it's likely to be a source of more victims for picking the frames to fill the page fault for another process. Okay, so that's priority. And then there's also what's called global versus local allocation. So that has to do with, do you limit the free frame source from within your own process, or can you grab it from another process? Right? Global says, well, all things go, right? Any process can grab frames from any other process. And certainly there's advantages to that, in that it's greater throughput, better utilization, and it's more common. But disadvantage is this less predictable execution time, because it may cost, you probably don't know the behavior of another process as well. Local replacement is you limit the victim to your own set, okay? And so advantage is more consistent per process behavior, but that doesn't imply better performance. It's just more consistent. And it probably doesn't utilize memory that well, because one process with more demand is still limited to that fixed set of frames, and whereas another one, a process with unused frames, can't be used for this purpose.
所以说，那个 replacement 选择的那个范围越大，那个对 utilization 会越好。
A higher chance of better utilization. Yeah, you would believe that. Yes, and in practice that's true, but then the behavior would be a little less predictable. Okay, I still have a little bit to go, but I think I'll finish up on Wednesday.